any questions? Projector. Okay, so quantiles, everybody's with me? What we discussed here, right? So let's go ahead and do the flooring and capping on the data using these quantiles, right? So you can see, like, I mean, we had a question on whether age has outliers or not, whether fair has outliers or not. So the best way of doing that is a histogram. How many of you know what is a histogram?
How straight your data is.
Yes.
You can see it in this document.
Right, absolutely. This is a distribution of your data on like certain bins, and you can create the bins using your own bin criteria, or you can let the tool decide, right? So I'm letting the tool decide over here. So in this case, what do you think the distribution looks like? I mean, is it a normal distribution? Is it a right skew? Is it a left skew? What do you think this data looks like? Right skew? Right. So like, you can see this distribution looks like this somehow, right? Right skew. When you have a tail on the right side, it's called the right skew. When you have tail on the left side, it has a left skew, but it doesn't look like very, like, I mean, it doesn't look like there's a lot of outliers. I mean, there's this thing that you can decide what to do or not, but I'm leaving it alone for now. Like, I mean, it's totally up to you. Now let's go and do it for the fair and then see how it looks like. How about now? Yeah, so you can see there is a huge tail, and the tail is coming in till here. There is one observation here, right? And this is no brainer. I mean, there are outliers in this data, right? Because you can see most of the observations are ending over here. The peaks are ending over here. Then there is spike here for some reasons, right? And then there is all the way this observation, right? So this definitely deserves an outlier treatment. Is everyone with me? So I was talking to Shinu, like on the second floor. One of the things that has come in is that people are very poor in the statistical knowledge in the interview today. So there was some interview happening today. Huh. And a lot of people don't even know what is a normal distribution, Z curve, all of those things. So you guys know, I'm sure you know, right? Are you sure? My favorite subject. So, I mean, I will tell you my personal story. I mean, not necessarily relevant in today's time, but when I went in the US, I mean, I did my chemical engineering, right? So BTech in chemical engineering, then masters in chemical engineering. But I never did anything beyond the core courses of chemical engineering there in the US during my masters, right? So I was doing all these statistics and numerical analysis, databases, and all of that, right? And few subjects where I really excelled, which I realized in my masters, was statistics, numbers, and all of those things. So from there on, I decided I'm not going to do anything with the chemical engineering. I'll just do, the entire data analysis and all of those things, right? So you have to have that level of passion to really enjoy the statistics, right? And we were looking at the back of the book to look at the T table, Z table. From there, we'll get the number. Has anyone done that thing? Yeah. So I mean, but statistics, I mean, you should understand very well. What is ANOVA, by the way? ANOVA you haven't done? So I will share one blog with you. I mean, it is there on my LinkedIn. I don't remember right now, but it's very good. I request all of you to do it. I mean, do all of us a favor. Um, it's called Easy Stats or something like that. I don't remember, but I will share that blog link with you. It is very visual. So you'll understand what is the Bayesian theorem, what is a naive Bayes, right? What is the conditional probability, all of those things. So I don't think you'll get the chance to do it later on. And some of those things are very fundamental. So if somebody can go and search for my post in LinkedIn, you'll find a statistics, visual statistics module. It's very, very visual, very, very like, attractive that you can go and look into, and then you can get more experimental. I will not have time to go in like a lot of those details because I have to cover the machine learning, but it's there and you can ask me any questions if there's something. Yeah. So in this case, fair definitely has an outlier. So what are we going to do with the fair? Let's see what we can do. So I'm using something called as a numpy np.clip. And then we are saying, what do you want to clip? I want to clip the fair from 0 and max value will be 249. Right? So I'm saying go like, do the outlier treatment on the fair by using something called as a clip method from the NumPy. And I'm saying, what are you going to clip on? Anything which is less than 0, because you cannot be saying that ship will pay or the Titanic company will pay you just to be on the ship. So the fare cannot be less than 0. Everybody agrees? Fare cannot be less than 0. And I'm also saying if anybody has paid more than $250, why $250? Because somewhere over here you can see like, we are finding this as a good sweet spot. If anybody has paid more than $250, we will bring down their fare to $250, right? We'll not remove those observations. We'll just make their fare as $250,000. Shall we try it? I will show you in the next one. If you don't want to do that, you can follow this approach. What is this approach doing? Dummy coding? No, it's not. It looks like a dummy coding though.
It is fast.
Mm-hmm. Hmm?
You're averaging the values between 1 and
Sorry?
limit. You're averaging the values.
Not averaging, not averaging. Yeah, but you're right. Like, I mean, think more. Yeah. Hmm. Yes, yeah. So let's go step by step, right? So it's looking at the same for loop for X in Titanic dot columns. It's going to iterate over the Titanic columns, right? What it's going to do, it will say, let's define the outlier limit. So I'm going to grab the first column and I will compute the first percentile and 99th percentile for those columns. And then I'm gonna like take the values and store in this object called outlier. So this outlier after this step will have two values. First percentile, 99th percentile for the very first column. What is the very first column? Whatever that column happens to be, like survive, I think, right? Then it's gonna come down and there is no if criteria. It is gonna do this 100% of the time. For all the columns, it's gonna do the same thing, right? So then it will say Titanic X. Now this X becomes NP numpy dot clip. It will grab the Titanic X and it will say clipped using outlier 0 and outlier 1. Outlier is nothing but this object. It has two values, first percentile and 99th percentile. So it will say, okay, I'm gonna apply the floor of first percentile and apply the ceiling of 99th percentile for all the observations. Is that clear? So before I run it, let's do this thing. I know I'm jumping around. Clip.
standardized.
No, clip is not standardization. That's what I'm trying to explain. No, it won't remove. So let's just do Titanic.describe. So you'll see before and after, like with any like treatment that you do before and after, right? So before pair is 512 max. Clear? Shall we do after now? Ready for the magic? Let's run this one. Has it run? I think it has, right? So now do the, it's too much zoomed in. Yeah, Titanic.describe.
249.
What changed? Did we drop any observations? How many observations we have over here? 891. We did not drop. And in this one, yeah, in this one also 891 observations are there. You can see there is some sort of haircut we have taken in the age as well. Age has been now 99th percentile, age was 65. So if you do a blanket, you will fix all the columns with the outliers, right? So that's why I'm saying I'm just going to do it for Titanic, fair. But you can see fair has been given the haircut that we really required, right? So there's no fair lower than 0, and there's no fair more than 247. Why 247? Because this number was there, I think around, I don't know why, I think we may have run it twice. That's why it's giving one more time. So, but 249 was the 99th percentile or somewhere in that vicinity. So that is used, and any values. So like the fair, imagine the fair was looking like this, 0 till 512, right? And this was our 99th percentile, which is 247 something after the treatment, right? So 512 becomes 247. 430 becomes 247. 320 becomes 247. So all those values which are higher than the 99th percentile, they're all made 99th percentile, 247. We're not dropping anything, we're not chopping anything, we're just imputing them with the 99th percentile and the first percentile. Is that clear? So this is the thing, and you can see this is a very gentle approach of fixing the outliers. If I go with the Z-score or IQR, I will chop half the data, or I will do the a massive outlier treatment, right? And that changes the complete story in my view, right? So you have to be doing outliers, but at the same time not being very aggressive in this approach, right? So duplicate I haven't run. Remember, I was running multiple times. I haven't run the duplicate. I knew that question is coming. So I haven't run the duplicate. So that's why. Is that clear, everyone? All good? Shall we do a Viva now on everything we've done? Okay. I want one of you to do the Viva for others. Who would like to ask the question? You get the brownie points for asking the right question also. Anyone who would like to ask the question on whatever we have covered till today? Don't be shy. There's no bad question. Anupam, you want to ask the question to others? Ask. No, don't do the recent one. Do the previous ones.
Uh, uh, what is the relationship between how do we arrive at the output? How do we arrive at the question with the relevant set of data? For example, I'm giving the answer.
Try again. You can frame your question.
So, what is supervised learning? Label data. And where is it used? Where is it used?
Label data, why is given the output predicted also. We have Excel features also. The relation is formed, but we can try the model.
You satisfied with the answer or no?
Two things.
Next person to ask the question based on whatever we have covered so far. Example of semi-supervised learning. Anyone would like to answer? I don't think we have covered semi-supervised, but yeah. Yeah, it's like, you're combining the learning little bit, but we haven't necessarily gone in the model. Yeah. Any other question? Let's see who remembers some of the tough concepts from today to ask that as a question. Ask the question. Face the audience.
In what cases should we do categorical values? Should we convert values to categorical values?
In what cases we should convert the values to categorical values?
You want have input data where you have where you want the Y output to be continuous, non-continuous. That's where we'll be using.
Where? Examples.
Example, let's say if I have a limited set of data wherein I have an answer of 1, 2, 3, 4 kind of a data of classification, that's where I use.
And it is-
Any other answers for that question?
And it is not a continuous data.
Sorry?
When it is not a continuous data, and where the category has an important role. For example, car brand type, we may have different brands. We can categorize or bucketize the classify as.
No, I mean, but the question is when you have a continuous data and you want to create the categories and then do the modeling on that. Is there any use case where you will convert a continuous to categorical and then do the modeling on that?
We have built it now, car brands.
Car brands.
I want to know the sales of the car every year.
Hmm.
Depending
But
on
what is your Y which is continuous here?
car price.
Car price is continuous. So then how will you transfer the price into the categorical?
Brand.
Mm.
Car brand.
No, exam scores. Exam score we can.
Exam scores. I think that's a good one. Yeah.
It's like below 30 means fail. Above
Yeah.
30 means pass, or we can. categorize like
Grade,
below 30,
grade. Grading. Yeah. So, I mean, how many people remember like how much you got? Like, I mean, let's say in your BTech, right? I mean, you remember the grade, whether I got the A grade or B grade or C grade or D grade, right? But we don't really remember that I got 97.9 or 95.3, you know, it doesn't really make sense also, right? So that's where this really comes in, that you can, instead of looking at the marks on a continuous scale, you have to convert the marks into the grade, A grade, B grade, C grade, and then you can say, okay, now I'm going to do the modeling, whether this person is going to get A grade or B grade or C grade. Does that make sense? Great question. One more question on like, you know, whatever we have covered today. Okay. What will you fill for the null values for categorical? Mode, or we can have our own like, you know, values. Okay, great. Is that clear? Any doubts so far from today's discussion?
How do you handle
Class imbalance we haven't spoken about. We'll come to it in the future class.
For the missing value, should we use mean or should we use median?
What?
Question.
Questions. Another question I have. I got it from one of my interviews.
Tell me.
If I am having two variables for regression, I have two variables x and y. So I don't know what will be my x, what will be my target. Maybe y can be my target, x can be my target. How I will decide what will be my target? Nothing has been written. I just given the data set. I need to decide small data set. I need to decide what will be my x, what will be the y.
Only values will be available. Only one values they are.
Only values I have given. They have.
Any random statement.
It depends on the objective.
Example, if you are.
No, you cannot assume that. You need to prove that this should be my this. This should be my y.
What is the business use?
So both can be interchangeable.
See, everything related to business. It is the behind of the regression. Define the behind of the four things behind regression. That is what I was asked this question.
And you answered it right?
I can answer in.
No, you just tell me right now.
There is an equation that just how to do that. There is nothing related to business. This there is a conceptual question. So there is a what is it? There is a concept called regression line. Okay, regression line is nothing but a base fit line. So we need to calculate two things: regression line of y on x, regression line of x on y. So and the formula also is having one thing that is called regression coefficient. So regression coefficient we need to calculate, and whatever x and y we have given from there, we need mean of x, mean of y, and regression coefficient we already calculated. And if we put both of this equation on these values, we'll get the equations. That is the first thing. Second thing is, whenever we'll be having regression coefficients, there is a property of coefficient, correlation coefficient R is it should be R should be like between 0 to 1. So if it is whatever calculated value, be regression coefficient, if we target for first example, if we create regression line of x on y, for that whatever regression coefficient I calculate, for that correlation of coefficient, if it is coming between that range,
Okay,
then we can go.
got it, got the drift. But you should have answered that person. Correlation does not mean causation. Correlation doesn't mean causation. You understand the difference? What is causation? What is correlation? What is causation? Does the X cause Y or Y cause X? That's the causation. Does that drive this or is it being driven by that? Right? What you're talking about is purely a correlation, right? I'm showing you some very, very strong correlations. Big Bang Theory, how to make baby, very, very heavily correlated. Explain me how. People who watch the Big Bang Theory and how to make baby. I mean, there's many, many funny ones, right? So Disney movie released, the amount of motor vehicles stolen, right? Popularity of first name Laurel and the number of costume attendants in whatever that means. I don't even know what that means, right? So I'll just talk about something more, right? There is like, this funny correlation. Yeah, this is a really good one. What has name Andrea to do with the consumption of cheese? They're very strongly correlated. Very, very strongly correlated, right? So what is the correlation here? I mean, I think somewhere it will be specified. The correlation R square is 95%. Right? So like they are superly highly correlated. But does Andrea have anything to do with the cheese consumption? At least I cannot explain that, right? There was one movie where how many times Tom Cruise appears in the movies and how many people die in the bathtub. Figure it out, right? I mean, why would that be correlated, right? So I think you should have responded that to that person that we need to establish the causation, not the correlation, right? So what he's saying is R square stronger this way or R square stronger going this way?
No, he didn't answer it. I got this answer from my book.
Okay.
I came back
Okay.
from the interview
Mhm.
and I checked what is how. After that, I started learning regression analysis from statistical perspective. There I got the answer what he asked and how to solve this.
Right, right. Yeah. For correlation. Causation. Causation can only be established by DOE, design of experiment. So two things are correlated. They're moving together. It doesn't mean that X causes Y or Y causes X. There's no definite formula to say that this is 100% being driven by this, right? Can you think about something else, which is like two things are moving simultaneously in the same direction, but they're not related to each other. They're being driven by a third factor, which is not part of your model at all. Any examples can you think about? Government experience, government employees getting
experience and
okay, but what are they being driven by? They're correlated.
salary.
Based on experience, they
Salary.
should promote.
Yeah, salary. Therefore,
It's a bad example, something that I just came out with, right? It's a bad example, right? Let's say the thefts in the summertime go higher. Thefts in the summertime go higher because it's like, very deserted place and temperature is very high outside. People don't go and all of those things, right? So afternoon thefts in the summertime. If I build a model of number of thefts and ice cream sales, I'll build a very good linear regression model that higher the number of ice cream sales, higher the number of thefts which are happening, right? So what I should do to reduce the number of thefts, cut down the ice cream sales, right? It's a great model, but the ice cream sales are being driven by the temperature outside and the number of thefts are being driven by the temperature outside. That factor is not there in your model at all. right? So that's where, I mean, the causation is not there. You have a correlation only. We'll come to it a little bit later on when we discuss more things as well. Yeah. Okay. So now let's talk about what are the standard processes that we go through, and we'll do a quick read. And this is the article number 28, folks. If you can quickly take a look, we can start to discuss some of the nitty-gritties of building a model, right? Article number 28 on my blog, linear regression, and focus your time and effort on these 6 steps. These 6 steps right over here. I think, no, I have already passed. I have already passed. These 6 steps: split the data, scale, training, test, create the instance. 28. If you can read, we can kick off the discussion on this. That will be the last topic for the day. And next Saturday is no class. How many of you?
What do we need?
The Pongal Makar Sankranti.
Article 28 or 28?
28.
20 to 28.
No, 28.
Okay.
उतना कैसे पढ़ लोगे भाई?
Someone ping.
No, it's you have it.
I was just trying to be your picture actually.
Is there anything you can search all the forces that are there? It's just like maybe I think we can find it way in the right direction. And I even see that. Almost there. Steam theory. Check it out. Steam theory. Thank you to Anupam to point me in the right direction. This statistics one is called seeing theory. Yeah. Seeing theory. Go ahead and bookmark this page for people who want to really understand the statistics, like, from the fundamental of the probabilities, all of those things, right? So for example, if you click on it, basic probability, right? So if I flip the coin, head and tail probability, what is the expectation, what is the variance, right? And it's all very, very visual. So you'll get the good flavor of what is happening there, right? Then you have the set theory, counting, conditional probability, right? All of that you can go through. And very, very easy probability distribution. Like these are some of the very, very fundamental things, right? You just read the central limit theorem. What does it really mean, right? So this is the one I was talking about. So I'll just put it there in the link, and Anupam has, I believe, already shared with you. So that is the one. And there's bunch more on my LinkedIn posts you can go through, but this is the one I remember. It's quite easy. Yeah. Like, I mean, are you seeing definition or like how to identify the children's definition? They are the correlated variables, so they're not necessarily required, right? So you have to really understand. No, in the sense of the dependent and the independent for the like the purpose of the model. Think about the user label is your dependent and your features are independent. Now within the independent plot, there might be features which are related to each other. Right? So for example, let's say your income in lakh and your income in 1,000. Right? They're exactly equal. So then you have to decide which one you want. We'll talk. So I hope everybody has gotten a chance to go through it. We're not doing the code right now. I'm just doing an explanation, right? So what are the 6 steps in modeling for the supervised learning particularly? The first step will be, so your data will come in as a DF, right? I'm assuming you will do all the data cleaning and everything, and your data comes in as a DF, right? The data cleaning flow we've already gone through. So the very first thing that you're going to do in most of the modeling steps will be, you need to separate your data into 2 different parts. Nope. Label and features separate. You need to keep your Y separate and X's separate. Is that clear? So in Titanic, which will be the label? Survived or not survived? Who survived, who did not survive will be your label. Your age, fare, which port they boarded the ship from, all of those are your X. So the first thing is to split the features or create the features and the labels separately. Why? Because your features will go through this process called standardization, normalization, or scaling. Now, who would like to educate us? What is this and why this is required? Hmm.
We are, we need to scale the first, why we need it? Because, for example, I am having, if my data set is having 2 features, one is called age, another one is called salary.
Hmm.
So if we are predicting something called future salary something. So salary is salary value is huge, means more value. It will be well. So to predict that, our equations or our model will be biased with the salary because it is having more values. So we need to scale all these values between certain range so that all the feature will be treated same way. So standardization is the same way because if we are if we use standardization, it is same as the like Z value, like x minus means x feature minus mean divided by standardization.
Yeah.
So if we do that, whatever value we are calculating, that value range will be not range. The standard deviation will be 1, mean will be 0 for that particular value.
Yeah. Okay, great. No, that's good. That's good. So let's say you have to find like a very brilliant person, right? And one of that person is studying in the 5th grade right now. And another such brilliant person is studying in the 12th grade. Can you take the 12th grade exam paper and give it to the 5th grader and say, okay, I'm going to assess you on that? That wouldn't be the right thing, right? So 5th grader needs to be assessed on the 5th grade syllabus, and the 12th grader needs to be assessed on the 12th grade syllabus, right? So that's what basically, I mean, relative to what they are, that's where you have to do the assessment, right? So this is the concept of the scaling. So what happens to Arpan's point? So there are variables which are, in the scale of 0.001 till, let's say 1 fractions, right? There are variables which will start at 10,000 scale, and then they will go up to 100,000 scale, right? And then there are variables which are in the millions to the billions scale. Scale meaning those values are really humongous. And some of these values are really very, very small. So what happens if you throw them as it is in the model? These variables have no shot at all. They'll be completely ignored by your model. Why? Because they're just minuscule. They're so small, so tiny range variables, right? It doesn't really mean anything in terms of those values. So that's where the scaling really comes in. And how does the scaling really help? That relative to your own variables value, I will bring them on the same scale. So I'll say, okay, if you are an observation of 1, what is your scale between 0 to 1? And then I will say, if you're 1, then you are max. And if you're this value, then you are min, right? And everybody else will be between the min and max in that range, right? Similarly, if you're 10,000, I really don't care what value you are. Literally, I'm just going to call you min, right? So you'll be min and you'll be max, right? And similarly for the million to billion, right? And then we're looking at in between values like this, right? And there are many, many ways of doing the scaling. So we'll talk about some of them. So there is a Z scaling. Z scaling is nothing but it will take your, we just spoke about that some time back, which is the standard deviation divided by that, right? So instead of looking at the values on the millions to billion scale of fraction values to bigger values, we'll convert all of them to the Z values. The moment you convert to the Z values, what happens to this scale? Most of the values will be between -3 to +3. What will happen to this one? What will be same? It will be going between -3 to +3. What will be happening to this guy? -3 to +3, right? So that's the beauty of the scaling, that no variable has undue advantage because of the scale, because of the size, right? The other way you can think about, like, let's say you are a boxer, right? So if I am fighting a small, tiny 5-year-old boy with a sumo from Japan, right? It's not a right boxing competition. So you need to have the same category. They say in the category of 70 kg, whatever that those ranges are. That's what you're saying. So we're saying with respect to your own values, I'm gonna scale you so that I can see what the distribution looks like for that variable. Similarly for the next variable and the next variable. So everything is scaled, and then they are much more apple to apple comparison now. Now what I can do is I can compare the utility of x1 to x2 to x3 to x4 on the same scale. Is that clear concept wise? How we do it, we'll discuss that later on. Yes, that's right. That's right. And it is even more critical for anything which is going to compute the distance We will do that some distance-based algorithm later on. Distance-based, like all the deep learning networks are distance-based, right? Algorithms like the KNN, right? Or sorry, k-means, right? Or any of those algorithms are all distance-based. How far away you are from that point, right? So if I'm 10 kilometer away versus if I'm 10 mm away, 10 mm will never have a chance against a 10 kilometer because 10 kilometers is a huge distance, right? So now, because I convert 10 mm to the z-score and 10 kilometer to a z-score, now it will be same that you are this z-score away from the mean, right? And that becomes a scaling criteria. So the very first step is create features and labels, scale your x's. We don't scale the y. Y we leave alone. We will take the x and we will scale them. Is that clear? First step in the process? Huh? You can do the z-score scaling. You can also do the min-max scaling. There are other scaling methodologies. So, I mean, when we say the min-max scaling, for example, each of the variables will be between 0 to 1, for example, right? Or 5 to 10, or 10 to 15, whatever you want to have in terms of the scaling criteria. So it's totally up to us. But the point is, if you use one criteria for variable 1, same criteria must be applied for the other variable as well. So you cannot have, I'm going to do the min-max scaling for this variable, but I'm going to do the z scaling for that variable, right? Because then the whole point is lost, that you need to be on the same scale and same criteria. Is that clear? Great question. So the second step in the process is,
not the embedding.
sorry?
It's not embedding, right? We're not.
No, it's not embedding. So it's no. I mean, we're not converting that original data. So remember, we have this data called DF, right? We did the X, we did the Y. X goes through the scaling process. Y remains as it is without scaling, right? So now let's say after the scaling, my X becomes X scaled, right? So I'm leaving my original data as it is. I'm leaving my original matrix as it is. The only thing I've done is from X, I have gotten to the X scaled, which is the scaled feature space. Clear? No. It has nothing to do with the linear regression. It is for variables to be having equal weightage in the consideration. Remember, like, 5th grader, 12th grader exam. So if I'm doing the competition India-wide to find out who are the most talented people, regardless of their age, for a 5th grader, I will give a 5th grade exam. So when I say the 5th grader, 5th grade exam, so that is X minus mu divided by sigma. So the mean score in that test for that exam is a certain mean and certain standard deviation. So I will see how far you are away from the average score. If you are like, way out there on the higher side, you are exceptional kid for the 5th grader. For 12th grader, I will have a certain exam, certain score, and certain mean and certain standard deviation. Then again, I'll say how far away you are from the average 12th grader. If you're very far away on the higher side, then you are an exceptional kid. Exactly. So you can imagine variable x1 is, 1st grader. Variable x5 is 5th grader. Variable x10 is 10th grader. And variable x12 is a 12th grader. So I'm saying I will give you a certain exam which is appropriate for you on your scale. Then I'll see how far away you are from the mean, right? Or what is your distribution, z-score distribution, right? Similarly, I will get a certain z-score here, certain z-score here. And then instead of looking at that original X, now I will have these z-scores or these scaled values in my feature space. You'll get when you do the experiment. Yeah.
Something similar to ratio. You calculate the ratio, compare.
Yeah, like, I mean, we're doing a transformation. We're not changing the data per se. We're just doing a transformation, mathematical transformation, right? Okay, let's go through. So this, all of this is after the data cleaning only. No, there's no data cleaning right now. I mean, we have done all of that. Now we're moving forward in modeling activity, right? So this is the first step. What is the second step? Split your data into the training and the test, right? So what happened, remember, I'm just trying to say the journey so far. DF became X and Y. Then this became X scaled. And this continues to be Y. Now what we're going to do is we'll say these X, let's do X scaled 70% and X scaled, sorry, 30% and Y 70% and Y 30%. Is this clear? 70-30 is just an example. You can do 80-20, you can do 60-40, you can do other things. We'll be looking at something else down the road as well. But this is a second step in the process, which is you take your data, you break it into the training and the test. And this is nothing but your train split. That you're going to train your model on a bigger chunk of data so that what are we trying to do over here? We are trying to do the behavior of this. Remember, we spoke about the supervised learning, that please learn the relationship between the X and the Y. So we are giving the model the opportunity that I'm giving you these Ys and I'm giving you these X's. Go ahead and figure out the relationship between the X's and the Y on the training data. Is that clear so far? Why is your label? It depends on your business use case. So in the example of, let's say, Titanic, it will be who survived, who did not survive, right? In the example of the salary prediction, salary will be your dependent variable or Y, right?
Somewhere
No, I mean, that is there. Yeah, so that again goes back to where we began our journey, that you have to first understand what is the business use case that you're trying to work on, right? What is your business utility will dictate what becomes your why or the label, right? And that label, you know which column. It doesn't have to be the very last column in your data frame. That label could be, the 5th column in the data frame, or it could be 15th column in your data frame. But you understand why this is my label, because I'm trying to modulate that variables performance as a factor of all the remaining features that we have in that data frame, right? So it comes in from your business knowledge. In this case, it's a baby data, let's say Boston Housing or Titanic. We know for sure that house price is my dependent variable or survival is my dependent variable or label. And the rest of those are my feature space. Is that clear? So now you have split your data into the training and test. 70-30, 80-20, 60-40, 50-50. I mean, we'll do some optimization there. But the main idea is that this becomes your training and this becomes your test. What do you think on a conceptual level will be the rationale for having a test data? That's right. So once the model has learned this behavior of the Y and the X's from this data, in the next step, I will say make the prediction only on the basis of X's. And you tell me what your Ys should look like, right? Or what your labels should look like. And then I will make the comparison with respect to what I know in reality those values are. And then I will tell you how accurate you are. If I build a model on the same data and do the validation on the same data, it's like, it becomes a self-fulfilling prophecy that you'll always get a great model because you build the model on the data and you're testing the model on the same data, right? So that doesn't work out. So we will come to that step in a minute. Till step 2, are you with me? All good? Yeah. After some time. The new data that is coming in during that time. Let's say you built a model right now. You've launched a model in production, right? No, not necessary. I mean, you can do like, from that time, but once you go in the production, it is already in production. So then so all of these are offline validation. And, this is like, something that you should sort of like, make a note of in your head. So offline validation happens before you launch your model in production, before we go in production, right? So we've done all the validation and everything, and we think the model is good, it's doing a beautiful job, let's launch it, right? Once the model is launched, then you must have a mechanism in place which does the online validation, right? Which is basically every once in a while, you get your Ys, which are coming in from your X's. and then you're going to validate those Ys vis-a-vis what you think really happened. So for example, let's say I built a default prediction model, right? When I launched the model, my accuracy was 98%. So that means it was good in doing the classification for 98%. Now, when I'm doing the online validation, meaning like, I mean, I've already given the loan to certain people for 1 year, and then out of those people, X% defaulted, and I see my accuracy has now become 91%. That's a degradation in your model performance, right? So it must be fixed. And that's where we will come into the, like, how we maintain the model in production. But right now, we're just talking about, let's build a great model and we'll launch that in the production. So we're in the offline method right now.
In fact, the initial once let's say we have created a model and it is giving us 98%. After the period of time, we know that it is going to degrade to 91% or 90.
We don't know. It may.
May or may not.
That's right.
We can further create a programming or a model which says
That's right.
if it reaches 90%, automatically update it to the new data.
That can be done. So you can have a automated retraining of the model and learning from the new data, all of those things, but we'll talk about that a little bit later on. So till step 2, everybody's with me. So what will be the next step? Create the instance of the model. Or it's a mouthful, instantiation of the model, right? You're creating the instance of the model. What do you mean by instance of the model? Yeah, which model you want to fit? And how would you know which model you have to fit? It will depend on whether my algorithm is a supervised or unsupervised. Within supervised, whether that is a continuous or categorical, right? Or within unsupervised, what I'm trying to do. So it's going to be a function of that. So the third step is create the instance of the model. So like you can imagine you are a chef in the kitchen, right? What dish you're going to make that day? Are you making a sweet dish? Are you making, something spicy? Based on that, you will pull in the right ingredients, right? So it's like, deciding on which model I have to really build, and only that instance I'm going to create. So in this case, for example, I'm saying I want to build a logistic regression model, right? So in the step 3, I'm just creating an instance or creating an object, which is going to take the sklearn logistic regression method, and it knows what is a logistic regression. It knows how to optimize that. But for now, just pretend that you know what is a logistic regression, right? So I've created the instance. Is that clear? Step 3? Yes, that's right. That's right. That's right. That's right. That's exactly right. Right. So supervised, unsupervised, within supervised regression of classification. Within regression, would I like to build a decision tree or linear regression? There are a lot of dependencies, which I'll talk about that in the assumption space, right? Great question. Nope, great question. And you will not be remembering those criteria as well. So what you do in real world is you build model 1, you build model 2, you build model 3 till model 10, and you compare all of them for that data, for that utility. And you compare.
So if, for example, if my data is not linear,
then you
there
should
is
not
no
be.
point of using any
You
other-
can still use it. Like, I mean, if I filled up, if I do a plain vanilla linear regression model, how good or bad my model is. Right. So we'll talk about that. And then this creates a leaderboard. Leaderboard. I was just talking about that. So you have a yardstick. What is a yardstick for linear regression model? You have something called as and I haven't spoken about that. So just take it with a pinch of salt, like error rate, right? The difference between the actual and the predicted values are error. Whichever model gives you the lowest error, I'll take that model, right? Do I always know which model is going to give you the lowest error? No, I don't know. You have to build all the different possible models.
Every set of data we have.
That's why you're paid big bucks as a data scientist. Otherwise, what is the point? I mean, if I tell you go fit the linear regression model and go take this data and do all of that, then your job is done. I mean, I can say GitHub Copilot, write a fantastic linear regression program and optimize and all of those things, and then that's it, right? So that's where the trial and error and art and science really comes in. You have to look at your data, you have to stare at your model metrics, you have to say something doesn't look right. I don't like this, right? Go back to the drawing board, change certain things, fit a different model, come out with that, validate the model, go back to the drawing board, and do this like 15 times. Then you have a solid model in your hand. Or you deploy like the big machine guns like auto glue on type of libraries, and they do this all this massive things for you. So when I talk about that, then you'll say, RP, you just wasted 4 days of my time talking about these things when machine can do all of this, but machine cannot do all of these things in real world. But there are libraries, auto ML libraries, which you say, okay, this is my data, give me the best possible model. And they will do exactly what I'm telling you. They will build model 1, model 2, model 3, model 4, model 5. They will compare the performance. They will rank out of them. They'll say, this is the best model, right? All of those things. But then our utility as a data science professional diminishes, because then you're letting the machine do all the job, right? Which is not good.
So
At the end of the day, that's what the task is. Right?
You have to explain. You'll be standing in front of the like your senior management to say, okay, I have this model, and what does this model do? And if you say, I don't know what this model does, but I know it does a fantastic job, then you are in deep waters, right? And very, very difficult to justify your point of view. So, and that's where the section of this is coming in, which is the, can you explain what you have done?
So I have in front of statistician in banks. So, for example, if there is no linear relationship, if I try linear regression, decision tree, and logistic regression, everything, they might ask there is no linear.
Force it to be linear. If you beat the data strong enough, long enough, you can make the data do anything you want to do. We'll force it to be linear. And we do it really in the BFSI vertical. Like, banking, 90% of, I don't know what is the situation right now, but when I was there in Citigroup, like 90% of the models will be logistic regression models. Why do you think that is the case? Like all the problems in the world are logistic regression models only? No. Exactly. For the easy interpretability and auditing and the compliance, and if third party comes and looks at your model, they understand what exactly your model is doing. I can build a very fancy model, but then the auditors came in from the federal agencies. And I say, I have noticed your model is discriminating against women, or I have noticed your model is discriminating against African American. Explain why. You are already like, looking at the billions of dollars of losses, right? So you have to have easy explainability as well. So that's where sometimes your hands are forced that you have to choose a simpler model so that you can explain. And there is no undue advantage to any group. Right. So that's why, all these models, logistic regression is a workhorse, right? Just because we have the XG boost or gradient boosting tree and all of that, it doesn't mean that we should ignore the logistic regression, right? So it's a very, very strong model. So moving on to the fourth step, then we are looking at the fitting the model. Where are we going to fit the model? On the X train and Y train. And I'm not using the term scale for the sake of simplicity. On the X train and Y train, I'm going to fit the model. What is this phase doing? It's trying to build this function, which is what is the relationship between the Y train and X train. Is everyone with me on this one? It has learned that behavior. As a next step, we will be taking this instance, which is now log. It has not only remembered what it came in with, but it has also learned the relationship of your data. Now I'll be using this same instance to make the prediction, which is log.predict. And I'm going to only give this time. Remember, we had X train and Y train and X test and Y test, right? This is Y train. So now I'm saying, since you have already learned the behavior, now make your own prediction. You tell me who is surviving, who is not surviving. And the model will come and say, I think this person is surviving, right? And this person is not surviving and all of that. And I know in reality who survived, who did not survive. Then I can assess the model performance, which is coming in as a next step. So the model has made the prediction. Using those prediction, I will now pass on the actual values against the predicted values, and we'll be doing a good comparison of how it looks like, right? This is the crux of any modeling exercise. Most of it is here only. And then you will evaluate basically. I mean, an evaluation, it depends on many different matrices, and I'll talk about that as we go into the modeling exercise. So in this case, we're going to use something called as a confusion matrix. We will generate the probabilities and all of those things. I'm not showing it right now, but we'll talk about that later on. We'll generate precision, recall, accuracy, all of those things. So who can tell me the 6 steps now?
Features.
Hmm.
Then we need to scale the.
So this is first, yeah.
Scaled features, we need to separate, we need to split, train and test.
Only scaled features or the Y also?
Only scaled features, not Y.
How many of you agree, disagree? Both. Only X. Only X is split or both? Scale you have already covered. So let's begin with the data frame DF.
X and.
No, data frame DF.
DF to X and Y.
DF to X and Y. Everybody is with us? So the way, let's just note it down over here, right? Without looking at it. So we are beginning with the DF. So Arpan is saying that I would go and in my step 1, I will do what?
X and Y.
X and Y. Okay. What else?
After that, I need to scale X.
Then I will do scaling of X. X scaled. This is all step 1.
Yes.
All step 1. Everybody is with us? 2 steps. Yeah. So let's say step 1, and step 1, 2, subpart 2, right? Okay. Then
Now I need to do splitting.
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 So now we are looking at the step 2.
X scale test, X scale.
This will become X train and X test.
I get Y test.
And similarly, Y will be split into the Y train and Y test. Scaled, right? Yeah, scaled. Yeah. So this is being fed into over here. This is fed into over here. Yeah. Okay. Is everyone with us so far? Step 3.
Model initialization.
We will create the instance
Model.
of the model. So that means basically as good as you create log, which is nothing but the logistic regression, and then you just say, okay, I want to do a logistic regression. Today I feel like doing a logistic regression. You bring in that instance, right? So that's what basically this is. Yeah. Okay.
Then log dot. fit
Then step 4 is what?
train.
We have to fit the model or basically do the training.
Yeah. Training.
Yeah. And how would we do that?
Said that if X train.
Log dot fit,
Yeah.
for example, and then we'll say X train, X train, and Y train, right? So we have done the fitting. Step 5,
Then predict. Log dot predict.
and then we'll do the log dot predict,
X test.
and we will bring in the X test,
Right, we need to assign the Y prediction.
and then you will have this value as, you know, your Y, Y predict, right? What is step 6 then? Step 6 is evaluate. Fantastic. And then you'll say, like, you know, whatever are the right metrics, I will pass on the actual Y test, and then predicted Y values. Is that clear?
Yes.
This is the flow overall. If you got that in your head, then you can do any modeling with any technique, right? That's the crux of it. And then we can say, okay, instead of looking at a logistic regression, I want to do a decision tree. Instead of looking at decision tree, I want to do a support vector machine. Instead of looking at the support vector machine, I want to do XYZ, right? Basically, all of them, they go through this flow only. Which one to use when? Yes. Yeah. No. Since we are in early days, and even like I mentioned earlier, I mean, you can do all of this using a auto glue on like library, right? The reason why you should not go fit everything in one go is because each of these models come in with their own sweet spot when they're gonna work, when not gonna work, right? So you should go step by step. So for example, you say linear regression, right? Then you can bring in a decision tree regressor, right? Because they all have very, very different algorithm. Even though they are all machine learning algorithms, but the assumptions are widely different from each other, right? Yes, and the way they do this separation or the prediction is also very different from each other, right? So for example, just to contrast, linear regression says, I will assume my model follows this relationship, right? This is the relationship. And decision tree says, I don't even worry about any equation. I don't know whether there is any relations or not, right? I'm a non-parametric method. Non-parametric method, meaning I don't assume a particular type of relationship, whether it's a linear, non-linear, hyperbolic, or inversely proportional, or whatever it is, right? As long as I know there's a relationship, I'll help you build that model for you, right? So, and so on and so forth. Random forest says, okay, I don't trust one single tree. I don't trust one single tree. I'm going to use 100 trees. And then I'll say, all of you 100 trees, you come back and tell me in my year only, what do you think is the right income or the right, the survival? And then I'll do a voting. And then based on the voting, I will then decide, what wins basically. That's right. So each of these algorithms work very, very different way, right? Then we are looking at more like boosting, where, one tree is helping another tree. So one tree says, by the way, can you help me? I'm having tough time predicting this guy. So the other tree comes and says, okay, let me help you in doing that, right? So they're all very, 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 very different algorithms altogether. So go back to the beginning of the day, right? So we said, okay, we will assume the data is there, right? Once the data is there, you'll go do the first thing. What is that first thing?
No.
Hmm.
Cheat sheet kind of something.
You have to first build the cheat sheet in your head, then go and look into this in the, I'm not kidding. So go step by step. And let's say if you look at all the models together, you'll get super confused. So you have to go one model, build one model, understand like the inner working of that model. Once you completely understand how linear regression model works, and you understand what are the pros and what are the cons of a linear regression model, then you say, okay, now let me try another technique. Because you know what are the pros and cons of a linear regression model, you can now compare and contrast, right? Now you say, okay, decision tree. I know these are the shortcomings in a decision tree, but these are the pluses in the linear regression, right? Or if I go and try a support vector machine, for example, right? So you must understand the algorithms, because even if I, let's say, use the Copilot to build the models, it will come back and give you a fantastic thing, the best model. Most likely it will do a better job than I can in building the model right now, right? Just by off the shelf optimization. But it doesn't mean that I go and choose that model. There might be some things that I need to be aware of about the data or the relationship or what my business requirements are, which will tell me, no, I want to have a much more visual way of depicting things, right? That's where I need to go with a decision tree. Or I need to have a certain things which can be an equation, then I need to go with a linear regression, right? Or I really don't care about the equation or this, as long as I'm doing a good job in classification, then I can go with the ensemble techniques, right? Or I really don't care whether it is one model. I want to combine multiple models together, which is called the stacking of the model. So you basically get the output from one model, second model, third model, fourth model, fifth model, n model, and then you stack them on top of each other to build a beautiful model, right? But if you stack them from the very beginning, and you don't even know what the linear regression does or decision tree does or something else does, then that's a problem, right? So go step by step first, then build that mental model later on. Are these 6 steps clear, everyone? I know this is a long day. Who would, yeah. Say it one more time. So you saying that if I do X split first, just a second. If I take X, so right now what you're doing is, sorry, go ahead. Yeah, so the process right now is that we will do the scaling first. We'll do the X scaled, right? And then we'll do the split. So you're saying I don't do that. I do the split first. So what do you think will be the outcome? So let's say X1 and X2. What do you think might happen? Yeah, how many of you agree with Aishwarya will have any impact or no? So instead of doing the scaling and then splitting, if I do the splitting first and then do the scaling, it will have an effect. How? Right, right. So you can try both ways, Aishwarya, but it will potentially have an effect. Why? Because of what exactly we just heard, right? Which is if I have a certain mean, certain distribution in my original data, and I'm building a model for my original data, not just for a small section of the data, right? So if I want to incorporate all the functionalities from my original data, I should do a scaling on that first. So I understand what is the mean, what is the standard deviation, what is the minimum, what is the maximum value, and then use that for the scaling versus doing the splitting, because then if you're lucky, your X1 and X2 may be exactly look-alike, right? That's how it should be. But X2 may also be like, for some reasons, not a fair reflection of your X1. And then you are beginning on the wrong foot from the very beginning, right? So that may be, but it may also work out better for you sometimes. So you can try both ways. It's not like, cast in stone, so you can change. Hide. For training, you have to give the Y value if it is supervised learning algorithm. So remember this step, which is right here actually, right here, right? So when we are doing the training, sorry, this one right here. So when we are doing the training, we have to pass on the Y value. Otherwise, how would it learn the behavior, right? When you're doing the prediction, then you don't have to. I mean, you must not pass on the Y values. It will not even take the values. It will say, I really don't need your Y values. All I need is, because I've learned that behavior now, I want your X. And as long as you give me your X, I can give you your Ys. You take your Ys, which I'm telling are the Ys, and then you make your comparison with the actual values, and that will give you the accuracy of the performance of your model. Is that clear? Any other questions? I know, we started a bit late, so we're ending a bit late, but I'm more than happy to answer any question. And next week is no class. 5 classes. 14th. 21st will be your next exam. Yeah. Exam will be moved to 21st. And we'll see. Yeah, I think if for exam it's too early, but before you wrap up, these are some of the things I'm asking you to do, right? Let's actually go to the blog itself, and it will be good if you can type your code in, because today we spent a lot of time just talking about the fundamentals of AI and ML and building blocks and all of that, right? At this space, I will be able to cover only 2 techniques, right? Which is not fair. So we have to accelerate, right? And how would we accelerate, since you have now the underpinning of what we're doing, why we're doing? So these are the things you can come read prepared, and you have read and you've done your coding also. I'm just highlighting what are the things you're going to read and be ready with the code. Linear regression, lasso, ridge, and elastic net. These are like the big brothers of the linear regression, like regularization techniques and the linear regression: lasso, ridge, elastic net. 30th, 31st, 32nd, and 35, 36, 37. These are the things you would like to definitely cover in the next class. So how to build a linear regression, how to build a logistic regression, how to use k nearest neighbor, KNN, how to build a decision tree, and more importantly, how to evaluate a regression model versus a classification model, evaluation metrics, right? And this will be very important right here, evaluation. And then linear regression will be covering the evaluation metrics as well, right? So if you see that we will be going through the data standardization as one activity in one of them, right? Standardization will be doing and will looking at the min max and the z scaling and all of that. So it will come in naturally. But that's the flow of things, right? What is there next after next class? So next class will be the second class. Then we will go into the unsupervised learning algorithms like a PCA, principal component analysis, and k-means, which is for the clustering. We'll be looking at your market basket analysis or the recommendation engine. We can look at other things. And then in the next class after that, we'll be looking at the ensemble techniques, which are like the random forest and all of those things. And then we'll step into the time series modeling, time series forecasting. That's very, very important class as well. Time series forecasting, which is like, combination of different techniques. And then in the last lecture, we'll be talking about how do you explain your model using, techniques such as SHAP and other things where you can explain your model performance, right? And then if time permits, I will also expose you to a free library, AutoGluon. So do not directly jump on this, otherwise you'll completely miss out on other things. But AutoGluon,
H2.
H2O is there, but H2O, I mean, I like the AutoGluon from AWS better, right? So it can do a good job for you, and you'll see like all the things coming together in the AutoGluon. Very, very like powerful package for building the model. So let's say you are hired, and very next day, because you've gone through this program, the expectation is you'll build a fantastic model. So if you were to do all of this, it will not be one day exercise. It will be many, many days exercise. If you go here, it will be few hours and you already have something. That's the beauty. PyCaret is also there. Some of those other libraries are there. But this is, very popular. It's a free library from AWS. So great question. So your assignments will be whatever are there, but I'll give you a brand new case study, for example. On a linear regression, I'll give you a brand new data set, right? On a logistic regression, lasso regression, all of them will be giving a brand new data set, right? And that is what you're going to submit starting second class. So second till the fifth class, we'll be having 4 assignments, right? So those will be your like the class material. And then we'll have your exam. And there's also thought whether we should do some Viva during the exam. So I don't know how that practically is possible or not, but Viva.
After the exam or before exam?
No, during the exam. I don't know how practical that is. A lot of you are very excited, no, for the Viva? No? Because I'm hearing that you guys are just putting the like the question directly in the chat GPT. And like all the places it is bold, the bold thing is also coming in all the places, but whichever is like, the way that chat GPT says, you're not doing any customization. Yeah.
Today's class, will you be giving any?
Today, no assignment. You can just let it all sink in, just absorb what we've discussed today. No assignment. Next class onwards, we'll have the assignment, yeah? But you have the assignment in a way that you have to type all the codes. Yeah. So I think one of the things I've done, people, in the last class, and let me see if it is there or not. So one of the things I've done in the next few lessons onwards is I've given you all the workings of the code as well, right? And then for making your life easier, what it is, you can copy paste without worrying about like, taking the image and all of those things like the Google Lens. You can just directly copy paste and run the thing, right? But then take that like, initiative. So go and ask, what does this do, right? Why this? why this optimization technique, and do back and forth with the AI. AI will be training you better than I can. But then you need to have patience. Okay. Thank you, everyone. Take care.